Alright, so this is my video on the Euler Lagrange two-stage method. First things first, a little bit of setup. Remember the first order differential equation standard form, which is dy dt plus p of t y equals f of t. And the core players here are going to be that f of t and that p of t. So our first stage of this two-stage method is finding the homogeneous solution, which is y of h. So how do we do that? Well, we set f of t equal to 0, then we separate our variables, or vars in this case, because that is shorter. Then we integrate both sides, and then we solve for y, and that y will be our y of h. So the second stage of this two-stage method is to find a particular solution, y of p. And how do we do that? Well, first things first, we're going to use a sort of outside auxiliary equation to help us, which is dv dt times y of h equals f of t. But then we're sort of going to follow these steps. So separate our vars, integrate, and then we solve for not y, v, v in this case. And the reason we solve for v is because v helps us find y of p, which is v times y of h. So we do all this to solve for v, and v is a critical component of y of p. And finally, we do the general solution, which might seem like 3 stages, but honestly, this is not really much of a stage since it's just adding the homogeneous and particular solutions. And that's how you get your general solution, which is generally where you want to end up. So first, we're going to start off with a small toy example. So remember differential equation standard form and the general steps that we're going to do. So let's get to it. dy dt plus 2y equals 0. And then we subtract that to y, so it's dy dt equals minus 2y, and then we divide all that by, well, I guess multiply by 1 over y, same thing, dy dt, which equals negative 2, and then we multiply it all by dt, 1 over y, dy, that one there cancels out, and then goes here, so that's dt, integrate, so that 1 over y becomes ln of y equals G's to 9, yeah, that, which equals minus 2t plus c. This c is going to disappear a lot, and you'll see it later. So we take both of these to, we both take the solutions to the power of e, and the ln gets canceled out because of this e, so we're just left with y, but there is no ln, natural log, over there, so we're still just left with that. Now, cool property of exponents is that you can sort of split it up like this. So these two are the exact same. And since e to a constant is also just a constant, we can simplify it like so. So there's our homogeneous solution. Now onto our yp, or yp, which is not t, dv dt times our y of h, which equals our f of t. So dv dt times our e minus 2t. So we can assume c equals 1. That's what I mean by that c disappears pretty frequently. So we'll worry about that c at the very, very end. For now, just assume it's whatever's easiest. So we multiply across by e2 of t, so it cancels over here. So t equals e2 of t. Then we multiply all this by dt, so we're left with dv on this side, t e2 t dt. Take an integrate both sides, so we're just left with v over here. And for this side over here, we're going to perform a integration by parts. So u equals t dv equals e to t. And there are much better videos on integration by parts if you are unfamiliar, made by very talented people on the internet. So, and now we solve this integration by parts. So that's t times 1 half e to t minus Oop, not, there we go. So v equals t over 2e to t minus 1/4 e to t, and then plus c, but let's just make that c equals 0 because it doesn't really matter right now. So with v solved, we can figure our y of p, which is v times y of h. So our y of h happened to be e times e to the negative 2t, if I am not mistaken, which I am not. And then we multiply that by our v, 2t minus 1/4 e to t, and we distribute that, but that just cancels with that, so instead we're just left with a y of p that equals t over 2. We should do that, minus 1/4. Now comes the easy bit. Y general equals y of h plus y of p. So that results in our e. So now we're going to use our c, now that we're finally using the general solution at the very end here. Is 2t over 2 minus 1/4. Are we done? Not quite, because we are given an initial condition, y of 0 equals 3/4. So y 0 equals 3/4, which actually just means t equals 0, y equals 3/4. So y of 0 equals 3/4, which equals 3e minus 2, 0 plus 0 over 2 minus 1/4. And 2 goes into 0 exactly 0 times. That 1/4 stays because it's a constant. And this ultimately comes out to be 0. So e to the 0, which equals our 3/4. We add 1/4 to each side, which just results in 1 equals c times e. Oh, no, e to the 0, but e to 0 is just 1, so c equals 1. And from there, we can finally come up with our final general solution. Y of t equals e minus 2t. Let me take a peek again. Plus t over 2 minus 1/4. Is that right? Yeah. All right. So that was our first toy example. Here's a slightly more difficult toy example. You know the drill. Remember that standard form is as such, and know the general order. So let's get to it. dy dt plus 2t y equals 0, dy dt equals minus 2t y, and then we divide that y. 1y dy dt, and that y is canceled. Then we multiply it all by dt. 1 over y dy equals minus 2t dt. Integrate both sides. Kind of screwed up that integral symbol. So that becomes ln y equals minus 2 times t squared over 2. And those 2's cancel out, but that minus remains. And so does that c, or because that's an unbounded integral, that c just sort of appears. So we're left with minus t squared plus c, and then take the e of both sides, and that ln cancels out. Y equals e minus t squared plus c. And as discussed before, we use the exponent special property to split up like this. And e to c is also just a constant, so e minus t squared. All right, so we have our homogeneous solution. Now to solve for our y particular solution, so let's do dv dt times y of h, which equals f of t, and our f of t is t to the third power, if I remembered correctly. So no need to keep that c, that's just the parentheses. T to the third, so dv dt. Let's just show our work of what we did. T to third et squared, excuse me, dv equals t to third et squared dt, and then take the integral of both sides. So that integral of nothing with that dv there results in just a v. Now I'm going to do something a little bit funky on this side. I'm going to split up that t to third as so, and I'll show you why in a little bit. And then I'm going to do something, another funky thing, which is I'm going to do u sub, but with w. So w equals t squared, and dw equals 2t dt, and dt equals dw over 2t. So we are left with that t remains, and w equals t squared, so that t squared becomes that. Then e to the w, and dt becomes dw over 2t, and these t's get canceled out. So we're just left with taking that constant out front, 1/2 square root w e w dw. Excuse me, and I'll show you why I didn't use u for u sub, because now we're going to use our u instead for an integration by parts. So u equals our w, and dv equals e to the w, dw, and v equals just ew, and that becomes dw. So v equals 1/2 integration by parts. So u v this v dw. All right. So v equals w/2 ew minus 1/2 ew, and don't worry about that plus c. So are we even good for v here? Well, not quite, because it should be v in terms of t, not v in terms of w, but w equals t squared. So now instead we have t squared over 2e t squared minus 1/2 et squared. With our v, we can finally solve for our y particular solution, which is t. Let's start with our y of h, which in this case is e minus t squared. Again, that constant disappears because we don't need it yet. We'll save it for the end. Yeah, okay, e to the negative t, and then t squared over 2et squared minus 1/2 et squared. We distribute this cross, and those cancel out. So instead, we are just left with t squared over 2 minus 1/2, which simplified is just t squared minus 1, like so. And that's our y of p. Now let's find our general solution, y general, which is y of h plus y of p, and our y of h. And now that we're at the end, we're actually going to use that constant plus t squared minus 1 over 2. And are we done yet? Not quite. Again, we still have the initial conditions to deal with, which is y1, y of 1 equals 1, y of 1 equals 1. So let's plug in y of 1 equals 1, which equals ce minus 1 squared plus 1 minus 1 over 2, and that just becomes 0 because 1 minus 1 squared is 1, and 1 minus 1 is 0, and 2 goes into 0 0 times. So this square only applies to that 1, but that negative is not affected, so we're still left with a c e to the negative 1, which equals 1. 1 equals c over e, which equals e equals c, which results finally in y of t equals e times e minus so plus t squared minus 1 over 2. And again, remember our properties of exponents, which leaves us with e1 minus t squared plus e squared minus 1 over 2. And that would be our final solution. And that is all for this video. I hope you learned something.